Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to introduce Sam Madden today. So Sam was actually in this area for a completely different reason. He came for a wedding, but we managed to sort of hijack him to give you a talk.
Not my wedding, not my wedding.
So again, I think he needs very little introduction. He's a professor at MIT in the CSAIL, in the computer science department. He's won numerous awards, including the TR35 award, the NSF Career Award, and then, of course, a whole bunch of Best Paper Awards. And probably many of you have seen, who attended SIGMOD this year, also heard the talk that he gave when he received the Test of Time Award at SIGMOD this year for the work that he did in his PhD at Berkeley on the TinyDB work. So again, it's great to have him here, and over to you. Today he's going to go big on big data.
Cool, thanks Vivek. So given this talk a kind of silly title, going big on big data, I know we're probably all pretty sick of hearing about big data, so I won't spend a lot of time talking about it. I'll give just a little. We have been running an initiative, a couple of initiatives at MIT under the heading of big data, this big data at CSAIL, and we have a big grant from Intel to do work in the big data space. So I'll talk just a little bit about my perspective on why big data is actually an interesting thing and not just sort of an overhyped trend. Before I start, maybe I'll say just a couple words about CSAIL for those of you who don't know about CSAIL. So CSAIL is the largest interdepartmental laboratory at MIT, so that means we're about 1,000 people, about 100 kind of professor level people, about 500 to 600 graduate students at any point in time, mostly focused on sort of computer science, very broadly defined. So CSAIL is Computer Science and Artificial Intelligence Laboratory. It's everything from robotics to hardware to HCI, much like, say, Microsoft Research. So it's a big place, and it's a pretty fun and exciting place to be a part of. So we all know, what is this big data thing? It's explosion of data coming from every possible source of things in our lives, from our cars to our smartphones to our computer games to our government to our cities. We have a tremendous amount of data, way more data than we know what to do with. So that's where big data comes from, this digitization of information, the tremendous availability of sensors from things like smartphones and location-based devices, access to cheap computation, and just increasingly connected devices, the sort of Internet of Things. So I listed some apps here, but rather than that, maybe I'll talk about a couple of applications that I think are cool big data applications, not necessarily for my own research, but that people around CSAIL are working on, just to give you a flavor of some of the problems that we're trying to solve in this big data at CSAIL. And then I'll really spend the bulk of the talk talking about my own research, but I just kind of want to start off with some big picture, big vision, sky kinds of things. So this first example is from somebody named Jim Michaelson. So Jim Michaelson is a mathematical pathologist at the Massachusetts General Hospital. So what he's done is assembled what he claims is the world's largest cancer patient database. So this is a database, actually a SQL Server database, you guys will be happy to hear, that contains information about 173,000 cancer patients. And it has a bunch of interesting information in it, all their medical records, all of the treatments that they have received, all of the billing and sort of insurance reports. If they died, it's linked to the National Death Registry. There's something called the National Tumor Registry, which provides information about the type and size and location of all the tumors in these patients. So it's a pretty interesting and rich data. Increasingly, it's starting to have genetic information in it. Anyway, Jim was very interested in the problem of medical costs. And so he started using this database to try and understand where medical costs go to in the Massachusetts General Hospital. And I think this is an interesting example because just to produce this graph took Jim and his team about 3 or 4 months. He's not a computational person. He did a lot of, putting data sets into Excel and making different plots and running different regressions, and it was very, very painful. And one of the things that he's come to us to ask is, can you help us to do these kinds of analyses over this data in a much more efficient way? So that's where we're starting to collaborate with him. But this result is his result that he came up with. So he asked the question, why? So this is the distribution of costs to treat lung cancer patients at the Massachusetts General Hospital. So the median patient, you can see here, costs about $13,000. The the top 10% of patients cost around $60,000. So there's like a factor of 4 spread from the median to the most expensive patient. Does anybody want to guess what the difference between these patients is? So it turns out these guys all die with about the same probability. Lung cancer actually is a terrible disease. People mostly don't get better from it. I don't know that, but I don't believe that that is a correlating factor here. One more guess?
The last one is our kids.
Whether they're yeah, I don't think it has anything to do with their lung cancer predominantly doesn't affect kids mostly. So these apparently, as far as I understand it, no. And in fact, so the other thing that often you might think and might be related to this is the sort of stage of presentation. Like if somebody comes in, very sick versus not sick, they might cost more or less. Turns out that doesn't matter either. What's that? It is the doctor, in fact. So it turns out that the thing is that there are about 6 doctors who treat lung cancer patients at the Massachusetts General Hospital. And if you have Dr. Jones or Dr. Smith, not their real names, you will cost 4 times as much money. Okay? So why? Because these doctors have a practice, which is kind of a weird practice. Like you come in and they will give you chemotherapy, give you x-rays every time you come in, whereas the other doctors are only doing this 1 out of every 3 or 4 times you come in. So these doctors just have different norms for what they think is the right way to treat these patients. In this particular case, Dr. Jones and Dr. Smith's treatment regime is not actually more effective. So this is, I think, kind of an interesting result. It's also, it's a data-driven result, and it's, increasingly our feeling is that medicine and these kinds of analyses, even, everybody's talking about genetics, and I think genetics are pretty interesting, but even absent genetics, there's a ton of these interesting kind of analysis problems. And these people like Jim Michaelson really, really, really want computer scientists to help them solve these problems. So it's actually, that's been a really fun collaboration that we've kicked off there.
So statisticians.
These statisticians. But I think that to me this is a computer science problem because this is this huge multivariate database, right? And there's this search problem over what combinations of variables are correlated with these outcomes that we're seeing, whether they're death or survival or cost or a whole bunch of other things. And there's all these theories. We can each take one of these theories, but if it takes a lot of manual analysis to test those theories, then that's not probably a very good way to think about this. And they don't apparently have tools that make it easy for them to kind of automate this search through this big database. It may be that this is not, I'm not sure that this is the world's hardest computer science problem, but I think it is actually, these kinds of multivariate analyses are probably non-trivial to get right. And my guess is that a lot of the explanations here are in fact complicated ones that are, many different things interacting with each other. All right, so here's another example, and this is a slightly different example. This is, let me tell you what the graph is showing here, and then I can talk a little bit about why I think this is an interesting sort of computer science big data problem for us all to think about. So this is a result from somebody named Andrew Lowe, who's a member of CSAIL, a very well-known economist. Some of you may know some of his work. He did this analysis of credit scores. So he was interested in understanding whether credit scores were a good predictor for default when you get a loan from the bank. So what he did is he took this database, was in this case a 1% sample that represented about 10 terabytes of data of all the financial transactions of customers from a major bank in the United States. On the y-axis here, on the x-axis here, he's plotted the distribution of credit scores. And then they're color-coded by whether or not the person defaulted. Was red being more than 90 days late on their loan, yellow being 60 days late, more than 60 days, blue being less than 60 to 90, 30 to 60, and green being less than 30 days late. So you can see that the credit score, if you sort of look at these green people, is not doing a very good job of separating the sort of defaulters from the non-defaulters. A lot of people with low credit scores are perfectly up to date on their loans, and the people who do default, although they're they don't have a very high credit score, they're sort of smeared over a pretty wide range of the available credit scores. So what Andrew did was built a classifier, a machine learning classifier that does a much better job of separating these people. You can sort of see if you draw a line through the middle here that the red people are cleanly separated from everybody else. So this model, does anybody want to guess what this model learns? So if I showed you somebody's financial records, what would you look at to predict that whether they were about to default on their loan? Yeah, okay, so how are you going to tell they just got sacked from their financial records? Well, if they stopped having direct deposits at the beginning of the month, that turns out to be a pretty good indication. So that's basically what the model learns, is if you stop seeing regular deposits, we're seeing regular deposits and stop seeing them. So this particular result I think is interesting because Andrew he's actually quite computationally, mathematically sophisticated. He's capable of using these models, but this particular, just running this model, generating the model takes a long time. He doesn't have tools that let him scale this, parallelize this generation of the sort of learning of this model. And so that's something we started to talk about is, doing this sort of parallel machine learning on these kinds of big data sets. And so here Andrew is actually the machine learning expert and the domain expert, but you could imagine different worlds where you'd have a domain expert and a machine learning person, and then there's systems people like us who are working on helping him scale these problems.
The previous example was extremely interesting and very actionable, but like this case, I mean, it's too late, right?
I guess it's too late, but if the banks had a way...
That's already the result, right?
Right. The question is, presumably, why does the bank care about this? Because they would like to understand whether they can...
They care not to give you a loan if they think they're...
Right, or they might want to intervene and say, boy, we gave you a loan, it looks like you just lost your job, maybe we should do... I mean, it's not... I think banks don't actually want you to default on your loans, right? It's not in their interest to do that. So if they can find some way to help you to... fix your situation, whatever it is, defer payments, who knows, right? Right, to get more of your money before somebody else gets your money, they'll be happy. Okay, thanks, David, for the cynicism there. All right, let me move on. So, okay, so you guys all know the sort of the big data, mantra of velocity, volume, variety. Our take on it is too big, too fast, too hard. But I think to me the kind of the interesting action in the big data space. I mean, we've all been working on too big and too fast, or volume and velocity for a long time. And these too hard problems, these cases where you need complex analytics to find patterns, or you need to really combine diverse data. I mean, these are the problems that we don't really know how to solve, and where a lot of the hard action is. And so, so our kind of take is that if we're going to solve these problems, what we really need to do is to work with people who are both the sort of algorithms experts, the people who have the domain expertise, the people in industry who understand the problems, to solve these problems. My feeling, and this is I think the most interesting thing about big data to me, is my feeling this like conventional view of the world as, there's database people and there's OS people and there's machine learning people is kind of it's kind of a screwed up view of the world. So I'm hoping we can, make some changes inside of CSAIL that reflect the fact that these groups need to talk to each other more. And I think, you look at the way things seem to be evolving here in the database groups at Microsoft Research, and I think you see a similar evolution of people recognizing a need to do this. So I'm probably preaching to the choir a little bit. I just want to say, before I move on to the more technical part of the talk, Microsoft Surrogate in particular has helped us to joined this Big Data at CSAIL initiative. It's an industry-supported initiative to sort of share collaborative research share and collaborate with a bunch of industrial partners. So we're really happy to have Microsoft as a founding partner of that thing. And as a part of that, one thing I'd say is, and you should talk to Surrogate, but we'd love to have people come out and visit and interact with us. And there's definitely, if you see problems that appeal to you or papers that we've written that you like, please make an effort to reach out. All right, so with that, I'm going to move to the sort of technical part of the talk. So one of the things that I've been thinking, and this is really more my research as opposed to the overview about our take on big data. So I think a lot of traditional database research has really focused on what I would call scalability and performance problems. There's this sort of prototypical System-Z Sigmod paper that says, we have a new storage manager for our database system, and it's, an order of magnitude faster than everything else that has come before it, right? And then you stamp out a bunch of performance graphs, and it's great. But one of the things that I think we don't do enough of is thinking about how we can make data kind of more accessible to users. So I'm going to talk about a set of what I would call data accessibility problems that are sort of 3 research results. One of them is Eugene Wu, who some of you may have seen, came out and talked about some of his visualization work. One of them is Eugene's work, but 2 other systems that I'll talk about. in a little bit more detail than Eugene's work. So the three systems. So my sort of take on this is, this is not what I want to say is big data systems is not about MapReduce, right? I think the conventional view of big data when you go talk to people outside of people who do research is that, well, what do I need to know about big data systems? I need to know MapReduce because that's the platform that matters. And I just, I like to hammer home the message that I think MapReduce is a perfectly great platform for certain kinds of things, but there's a lot more to be done, and it's not the silver bullet here. So I'm going to talk about three kinds of things. One of them is Eugene's work, which I like to characterize as helping users understand why answers are what they are in their data. So that's the system called DBWipes. Another is some work we've done on crowdsourcing and using people integrating people into databases. So this is this system called Quirk. And then finally, I'm going to talk about an interactive data visualization system we built called MapD that uses GPUs to really, really efficiently visualize and interact with large data sets. And I'll give a demo of that. So with that, maybe I'll just take a couple minutes and are there any questions? I know I went kind of fast through that, but. So on to the good stuff. So DBWipes. So here's my take on DBWipes, and this probably is not Eugene's take on it. So maybe you'll get a very different story. First of all, I think visualization is really, really important, and it's something that I've started to feel like is something that we as a community. There are some interesting data processing problems that underlie visualization. Obviously, it's kind of probably the first place that a lot of people start when they're analyzing a data set is just to look at it and understand what it looks like, right? Plot it, right? You make some distribution, right? And one of the things that often you find with visualizations are outliers. So data points like these guys up here. What is it about these people up here who have very high credit scores and yet defaulted on their loans, right? These little red dots that you see there on the upper right. So what we're trying to do in DBWipes, I think of what's important about this tool is it's a tool that tries to help you identify why outliers exist. So what do I mean by why? So given a visualization, which would typically be generated by some computation that you ran on some underlying data set, right? What we're trying to find in DBWipes is to try and find a predicate. So you've got input data set, you've got output data set. You're trying to find a predicate over the input data set that when applied, a filter that when applied to the input data set will make the outliers in the output data set go away, okay? So why is this an interesting question? Because you kind of want to understand what are the properties of the inputs that cause the outputs to look bad, right? And that's sort of what these predicates, if you can find them, will explain, right? And this is a challenging problem because these data sets are often, like this data set is this huge multi-dimensional data set. It's got hundreds of different dimensions. And so this search problem over the input data set is quite complicated, right? You might have to look at sort of all correlated sub-ranges of, all sub-ranges of all input attributes that, might potentially be the ones that cause some data to be outliers. For certain classes of SQL queries, for example, if these points were generated by doing a group by and then taking an average in the groups or something, you may be able to find efficient ways to figure out the relationship between inputs and outputs. But in general, if this is a black box function like it is here that produces this visualization, solving this problem is challenging. Okay, so that's what this DBWipes system tries to do. I'm going to sort of go through the system by showing you a little demo, a little interactive demo of it, rather than going into too much technical detail about it. But we have a VLDB paper coming out in this upcoming VLDB that discusses this problem and gives a preliminary solution to it. I think probably our algorithmic, the sort of algorithm we have for doing the search problem, it could be refined, and if people are interested, I think it sounds like an interesting problem. I'd love to talk to them more. This is Eugene, by the way, made me promise that I'd show a picture of him every time I presented his work. So that's Eugene for those of you who didn't see him before. Okay, so here's the interface. So did he show this before? He didn't show it. Okay, good. All right, so this is a data set. It's actually not a particularly large data set that was collected from, it's a set of sensors that were measuring light and temperature and humidity in a building. And what this visualization, the blue dots here represent the temperature variation throughout the building over a 4-day period. So the peaks and valleys represent the building as it warms and cools in the morning and afternoon. On the bottom, we're just plotting the variance. So each one of these points is actually generated by taking an average and a group by of a whole bunch of data points, right? So on the bottom here is the variance of each one of the points on the top, okay? So you notice that in the variance there are some interesting outliers, some points where the variance is very high. So you might say, well, what was going on with those particular sensor readings? What was the variance? So what DBWipes lets you do is select those points, and you can tell the system that those particular points are outliers in some way. You can either say they're just wrong, I don't know why they're wrong, or you can say I think these points look higher than I would expect. You can also give DBWipes some positive examples, so you can say these points down here, they look more like what I would expect. So you can select those and say those are good outputs. Okay? So you sort of give it this information, and it uses this to solve this, this search problem, basically, of searching over the input data set in order to find points that if you were to remove them would cause the bad points to go away and hopefully would leave this good set in as it is. Okay? So when you run the system, it gives you a set of predicates that are sort of like this. It basically searches through the space, finds ones that remove all the points, and then runs a simple decision tree basically to try and describe what the properties of those points are that if you remove them would fix the outlier problem. So if you click on the first one of these things here, for example, you can sort of see as I toggle back and forth that the first one of these makes all the variance go away. So we did a good job of finding this. What is this predicate in this case? Well, it says, you guys probably can't read it, but it says not mode ID equal to 15. So these were these little sensor modes, and mode ID 15 is one particular device. So in this case, sort of the explanation is that there's one device that's malfunctioning during these time ranges. And it turns out, actually, if you drill into this a little bit more, it has something to do with the voltage on the device. So if this device's battery, as it starts to run out, the voltage drops, and when the voltage drops, it starts producing haywire, crazy readings. Okay? Questions about that? Yeah. Okay, so it's sort of like what I described before. So what we need to do is we go into the input data set, right? And we need to search through. So we know for those inputs that the user highlighted, for this set of inputs that the user highlighted, right? We know we can figure out what all the points that contributed to any of those are. So those are the points that we sort of need to search through because those are the ones that we might need to eliminate from the data set. So then the paper proposes 3 or 4 different kinds of search heuristics, basically. Like you basically what you want to do is to, so the sort of, the most naive algorithm, what it would do would be to take randomly subdivide all those input data points into a good set, into a candidate good set and a candidate bad set. And then you would rerun the query over the candidate good set and the candidate bad set, right? And then you would sort of, you'd figure out whether which of those 2 sets was better, and then you would recurse somehow. Or you could do this in kind of a bottom-up approach where you could pick 1 point at a time. You could remove all the points in this entire set and then add them back in 1 point at a time until you found the one that, most eliminated these things and, best kept these good points in place. So you can does that kind of give you a sense of, and you can imagine a whole bunch of different kind of, search algorithms in between that in order to, navigate through the space and find the one that best explains the outlier. Yeah? Yeah, so in fact, if you go look at the paper talks all about we started working on this problem because Eugene's past work was really on, he was working on provenance for these array-oriented database systems, and then we started talking about, the thing that we think is interesting about this is like provenance, but where you're doing these aggregation operations, so it's provenance across aggregations, where the functions are not necessarily simple SQL functions. So if they're simple SQL functions like average, it's a lot easier because I can sort of, or take an even like max is the obvious case, right? If I'm asking for the maximum, I want to make the maximum go down, well, I can trivially identify the highest point in the input data set and remove it, right? But
so when you come up with these predicates, do you run into the issues of overfitting the data, and if yes, do you control it?
Sure. I mean, we're using a decision tree algorithm basically to build explain the predicate. And like any decision tree algorithm, you have to kind of cut it off at some point. You don't want to generate too much of a predicate. In fact, you can see the way that we've solved it here is to basically prefer emitting predicates that have fewer clauses in them. That actually these are 5 candidates, and they get progressively more complicated as you go on because the system is kind of proposing things that are like, it's basically overfitting the set of input points. So I think there's a classic overfitting problem here. Yeah.
Can this be viewed as a classification problem where the points that you've identified are like examples?
Yes, it could. And we in fact tried to use a classifier for this, and it didn't work very well, and I don't remember why. Sorry. We did think of doing, I mean, we tried using SVMs or something, and it didn't work, and it may be that we didn't use them right. You know, oftentimes there's a lot of kind of art in getting these models right, but yeah. Okay, so what Eugene is working on next, which I think is pretty cool, is to then build this into a general purpose visualization language. So what he's trying to do is to come up, he's got this sort of simple declarative language. There are several people who are proposing these kinds of grammars of visualization now. So he's building his own little grammar for visualizations that looks like this. It says, you know, I've got some data set, and I can specify the, you know, X and Y axes and what the scales look like and what the colors, you know, how colors correspond to different attributes in the input data set to make pretty looking pictures like this. But what I think is really interesting about this is he's now integrating this, what is essentially a provenance system, into this thing. So there's a relationship between each point in this visualization and each point in whatever the input data set was that was used to generate the visualization, right? And so what the idea is, this doesn't work yet. He's very close to having a demo, but it's not quite there. The idea is that you'll be able to, for each data point, sort of work backwards and see what inputs it were in the input data set that corresponded to it, as well as do this sort of DBWipes thing where you can select some outlier data point and it can, you know, run the analysis that we have in order to sort of identify common input predicates. So we're trying to build sort of a general purpose visualization tool that lets people write their own visualizations. This demo that we had here is sort of a canned visualization, not a, you know, it's not a flexible visualization system, but we're trying to build this kind of support into a visualization engine. So I think this is a really cool problem, and we're something we're kind of starting to push on a little bit. So, all right. Okay, so that was DBWipes. What I'm going to do now is shift gears a little bit, so that sort of, you know, thinking about how do we make big data accessible. Well, visualizing data is an important thing to do. Another thing often that you run into with these systems is that, well, you need some way to take human input into account. So in data integration systems, for example, this is, you know, you need this support, right? You need the ability to ask a human which of these things is correct, right? And so even if you have some automated tool that does a good job, you're going to want something that can help to, you know, kind of take human input. And so my student Adam Marcus spent a couple of years actually working on building a crowdsourcing system that we call Quirk. And so I'm going to talk just about one kind of result that we got in that system and give you a little bit of an introduction to what Quirk can do, okay? So Quirk is mechanical Turk plus querying or something. All right, so you guys probably all know about crowdsourcing. The classic crowdsourcing system that all the people seem to do research on anyway is Mechanical Turk. This is a system where you can pay people pennies to compute simple tasks, like go look up something on the web for you, okay? There's lots of other crowdsourcing platforms out there. There continue to be more and more of these, and they vary in the types of tasks you can ask people to do. Some of them are like TaskRabbit, like interact with the physical world. Some of them are, you know, more, you know, design artsy tasks, like build a website. You know, there's a whole bunch of these different platforms. Turk is appealing because it sort of has it has a programmatic interface, and you can ask people to do simple things. And in particular, you can ask people to run. What our observation was, you could actually write tasks that would let you do sort of database kernel-like things with people. So that's what we did in Quirk. So our question was, could we use people sort of as the inner loop of a database? So you know, suppose, whatever, I want to find, you know, I have a table of people, and I have some unknown values in that table. I might want to use Mechanical Turk to, you know, get people to supply the phone numbers, right? So this would be have people go do web searches. But the interface that we're going to provide is one that's a table-oriented interface. It's like a database. You can say, here's a database, and here's some unknown values, and then the system will automatically go out and post these tasks on Mechanical Turk in order to be able to get the supply missing information. Okay, but there's other things that you might want to do with the system, right? Like you might, for example, want to you know, rank people, right? So maybe I want to say, who are the ugliest people at Microsoft Research, right? So who knows what the answer would be, but, you know, you could show people pictures and get them to run that as a ranking function. And that's something that, you know, it's a matter of personal opinion. You're never going to be able to get a computer to do this, but, you know, it's a task that, you know, maybe you want to actually use a computer to do. More seriously, you know, I think people are often faced with very subjective ranking criteria, and, you know, if you're trying to prioritize what's the most important, you know, bug to fix in a project or whatever it is, you could imagine, you know, having programmatic interfaces to groups of people that would let you do that. All right, and then finally, you know, maybe there's kind of join-like operations you want to do, like is S Chowdhury the same as Surrogate C, right? And you have these two pictures and they're labeled, and you have to decide whether these things are the same or not. This is basically a data integration, you know, entity resolution problem that, in many cases, people are just going to have more context, and they're going to be, you guys would all be much better at solving that problem than any algorithm ever, right? So probably. All right, so what we built is a simple SQL-like interface. It looks a lot like Pig, if you guys know Pig. You can say things like, for each researcher or professor, generate name, comma, get phone of name. And this get phone is a UDF that we have a simple, a simple domain-specific language that lets you describe what that UDF looks like. It will, go and result in tasks being posted to Mechanical Turk. You can say other things like if I've got pictures of cats and I want to know which ones are smiling, I can say filter the photos by some other predicate, right? And so we have this, if we had a table like this of images, right? So this is just an example of the syntax. So we have task types, so there's a filter task type, there's some prompt that has some HTML in it, and then there's some way to combine input from multiple users who, because users might disagree. So oftentimes in these systems, you need some way to sort of reconcile multiple different users' input. Right, I'm sorry about the examples here. These are the world's silliest examples, and these are Adam's slides, and he just came up with the world's silliest examples. So unfortunately, it's only going to get sillier, so you kind of are going to have to bear with me. But anyway, so this is an example of the kinds of interfaces that users we'd create these hits that would look like this, that would be posted to Mechanical Turk. So when you start thinking about this problem, actually, there are a surprising number of pretty interesting problems here that it's not obvious how you're going to solve all of them. Like, how much should you charge people? How much should you pay people for each one of these tasks? And what's the relationship between payment and quality and response time? And how many workers should you get for each task? And how do you determine whether a worker is a good worker or a bad worker, or whether a worker is trying to spam you or take advantage of you or not? And what's the right user interface for building these? And what if you batch lots of these different tasks together into one of these hits, or if you do them as separate ones? How do you deal with algorithms like joins that sort of are, the naive, or sorts where they're sort of super linear in runtime, and it seems like even for small data sets, you could quickly end up having to do a lot of tasks to do anything very interesting with them. And what's the right ordering of operators, and is it different than in a conventional system? And how do you build a user interface that tolerates the fact that responses are going to come back slowly over days or hours rather than right away? So there's lots of interesting questions. We've worked on a bunch of them. I'm going to talk today just about one simple example problem, which is ranking a list of items with people. Okay. Right. So ranking, I've already given a couple examples of ranking, like rank researchers or papers or bugs by some report. But there's lots of cases in the world where we need people to rank things, or the web. This happens all the time, right? So Yelp, you rank restaurants by their ratings. Amazon, you rank or rank things by rank books by their user scores or likes. So these interfaces actually suggest one of the ranking algorithms that we're going to think about, which is this the idea that you can ask people to give a score and then rank things by their average score, right? So the other way that you might rank things is to I'll show you. Let me just show you, since I just started this very silly example. Okay, so this silly example is, suppose you're stuck in the wild and the wilderness, and there are dangerous animals all around you. You have to figure out which ones are the most dangerous to avoid them. Okay, so you want to sort animals by dangerousness. All right, so these are some example animals, and we're going to show them to people and run them. So this is a very simple. This is a very silly example. The reason we picked it is because we wanted to pick some examples of things that we thought people on Mechanical Turk aren't likely to have a ton of domain expertise about, and that everybody can kind of, like people mostly know what different animals are. I mean, maybe people don't know that this is a lemur and that's a hyena, but people have some sense of animals. They can look at them, they can make some assessment of them. And we asked them some different questions, like we asked dangerousness, which is kind of a weird thing to ask about animals. We also asked them about size, which we thought was an easier thing to ask. So we asked them some different tasks that were, so we sort of were hoping that this would be a domain that wouldn't be too polarized by experts and non-experts. Anyway, so we built these two interfaces. So the two interfaces, one is a rating interface, as I already suggested. The other one, we did a direct comparison interface. So this is, I call this the hot or not interface, right? But basically, you can pairwise compare all the animals to all the other animals, and you'll get some ranking or some result, right? These things are kind of both of these are kind of interesting, right? Because if you just ask everybody to rate some set of animals and give a score for it, you haven't actually compared every animal to every other animal, unless you maybe if you asked everybody to provide a rating for every animal, you could then argue that you had a good ordering of things. But you're not really comparing one animal to another. You're just sort of getting one rating per animal. In this case, you are directly comparing animals to each other. And so in that sense, maybe you're getting more information. But the interesting thing is that people may disagree, right? So some people might say a hyena is more dangerous than a hippo, and some people might say a hippo is more dangerous than a hyena. And so you get these conflicting answers that actually, when you think about sorting things, makes the world sort of unclear what the right sort is. You have this sort of, people in theory have actually studied this problem, this sort of noisy comparator problem, and it's. It makes it difficult sometimes to apply naive sorting algorithms, like if you apply a quick sort where you pivot on one animal, pivot on is dangerous, is not dangerous. You can end up with these kind of weird incongruities, basically. So anyway, that's one sort of interesting result that came out of this. The other thing we looked at was batching. So we built these interfaces where we let people compare multiple animals to each other or rate multiple animals at once, which is one way to deal with this super linear complexity. You present multiple things to people. And we looked at whether people would, we sort of looked at people's tolerance to, this is kind of a social science phenomenon, but how tolerant, how many people, how big are the batches that people will tolerate? And as you go to bigger batches, how does result quality fall off? And how does response time fall off? And we looked at a bunch of different kind of results like that. So what I'm going to do is I'm going to give just give you two results from the paper. There's a bunch of these other things that are reported on the paper. So the first one is the quality of results. So how does comparing compare to rating as a sort of way of ranking items? So the way we the way we evaluated the ranking is to use this thing we call Kendall's tau rank correlation. So we took what we believe to be the true answer for a set of questions, and then we computed the ranking that our system generated using human workers to the true answer. And we used this measure called Kendall's tau, which basically gives you a number between -1 and 1 that's in a sort of the agreement of two rankings with each other, just is a measure of how many items are out of order, basically. Okay, so we took the true answer, we compared the answer from the crowd, and we looked at these two interfaces, the comparison-based interface, where we compared every item to every other item and then used majority vote for workers. So we used workers. Every item, I think, was ranked by, compared by, every item was eventually compared to every other item 3 times, and we took the majority vote. In that case, the first task we tried was a set of squares, okay? So if this was meant to be a super easy task that everybody would get right, and in fact, in the comparison interface, everybody does get it right. We perfectly order the set of squares compared to the ground truth. This tau rating thing where we ask people to rank the size, we show people the smallest square and the largest square, and we ask people to rank on a scale of 1 to 5, which, how big is this square, doesn't give a perfect answer, but tau 0.8 is actually pretty reasonable. The kind of interesting thing about this rating thing is that we only have to look at every item, sort of rank every item once. We don't have to rank all pairs of items. Okay, so it goes from a quadratic to a linear time. So we then looked at a hybrid algorithm where we tried using rating to sort of get things mostly in order, and then we used sort of local comparisons in order to reorder things up to a fixed budget, basically. And we saw how well you could do for a certain budget with that kind of using, if you're willing to spend a little bit more money to fix things up, how much better can you do? And so you can see that so this is the tau of 0.8, which is the rating-based interface, and this is the comparison-based interface, which is perfect. And then we sort of saw so this tau 0.8 takes whatever it is, in this case, some number of tasks. So it's in this case, I think it's per item we have 9 tasks, and here per item we have 81 tasks. So it's the comparison interface is a square is n squared, and you can see the comparison interface. Basically, as we add more tasks, its quality improves. So we were able to come up with this interface that was able to kind of progressively improve its quality. Eventually, and interestingly, it gets to a perfect answer before it has actually used up the same budget as this comparison-based interface. Okay, so we then asked people, we did some silly things like we asked people to rate animals by dangerousness. This is the rating that people came up with. So flower, ant, grasshopper, rock, bee, turkey, dolphin, parrot. I don't, it's some of them, they basically make sense, the ranking that people came up with. Why, whether we all would agree that a whale is less dangerous than a panther or that a turkey is less dangerous than a dolphin, I don't know. But, people did actually do this and they came up with a ranking for animal dangerousness that seemed kind of reasonable. Yeah, well, what people are, or just what people's personal fears are, right? There's probably some people who are really afraid of sharks or something, right? Yeah, skunks are surprisingly dangerous. Yeah, I'm not sure I would call skunks all that dangerous, but yeah.
More people than anything else on the list.
Yeah.
That's right. Hippos are I think, probably the most dangerous by lives lost, right? Although, on the other hand, most of us don't interact with hippo. There's also probably a bias here about where these people are coming from, right? Like most of us don't have occasion to interact with hippos on a regular basis. So, yeah. Whereas you might have a skunk problem, right? Okay. All right. So I think we looked at some other interesting kinds of questions about whether we could detect whether or not a particular question was ambiguous. One of the things we were interested in is whether we could learn that a problem was people were not doing a good job of answering a question, or a question was hard for people to answer. And so we phrased a set of questions on animals from less to more ambiguous. So animal size we thought was a low ambiguity question. Dangerousness is a medium ambiguity question. And then to ask something that's completely ambiguous, we asked them, how likely would you be to find this animal on Saturn? Okay, which is a question that makes no sense, right? And the idea was we wanted to understand, we wanted to see if we could come up with a metric that would in fact let us understand whether the question we were asking made no sense to the people who were answering it, right? So we used this metric called Kappa, which is just a measure of agreement, rater agreement that, again, basically varies from 0 to 1 based on how much people agree. Okay, so basically, if you look at squares, people agree most of the time on the size of squares. And actually, on animal size, we were happy that they basically agreed on animal sizes too. People seemed to understand what these animals were and be able to rate them. And you can see that, and if you ask people just like to pick a random number from a list, for example, you see that they don't agree very much, although they agree a little bit more than 0, which is surprising. So I'm not sure what that is. But you can see that, in fact, this is a pretty good metric for detecting whether a question is completely ambiguous. Okay? So the kind of interesting takeaways are, first of all, we can use this rating versus batching interface, the rating versus sorting interface and the hybrid or comparison interface and the hybrid version of this, as well as batching, to reduce the total dollar cost number of questions we have to ask pretty significantly. And we looked at a bunch of different metrics to understand how good a job we're doing using this tau thing, as well as this notion of this notion of Kappa, to see if we're asking a question that users don't understand. So is this big data? No, it's not really. But one of the things we have been, in the sense that it's hard to scale these interfaces up to large amounts of data. But one of the sort of natural questions to ask is, how would you integrate a system that uses people into a larger system, right? So one of the things we've been looking at is whether we can use these crowdsourced data to, for example, train a classifier, which could then be used to do predictions. So could we, build a predictive model that would allow us to estimate, based on the parameters of animals, which ones are dangerous or not, by using crowdsourcing to do this. So this is kind of an active learning problem. So we've kind of been asking, we started to ask the question, well, okay, let's take that as the starting point. Can we figure out which crowd workers we should ask to give us information that will allow us to, or which questions we should ask users about, which, say, animals in our dangerousness algorithm, we should ask users about in order to best improve the accuracy of a classifier. Okay, so the intuition is that if you have a classifier and you have some items that you haven't labeled yet in your training, in your set of items, right, and you can ask the crowd to label some of them. The ones you want to ask about there are lots of different proposals you might come up with. You might say, I want to ask about ones that are close to the margin, between dangerous and not dangerous, if I'm just asking a binary classification problem. Or you might want to ask about the ones that the algorithm is most uncertain about. Which, and what do we mean by uncertain? Well, we had a specific definition of uncertainty where we tried leaving, we tried taking the training data we had so far, leaving, iterating over different subsets of it, and then measuring whether items classification changed from different iterations. So this is a variant of this non-parametric bootstrap to estimate the uncertainty of certain items. And we came up with some algorithm that does a pretty good job. So the takeaway here is, I don't want to go into too many details, but kind of the takeaway is there is this big data connection, which is you want to figure out how you use people in these database systems. And oftentimes this could be for a machine learning task or even just for to supply a bit of uncertain information in a data integration task. And I think it's really interesting and important for us to think about how we integrate these things together. So does anybody want to ask any questions about that part of it? And then basically what I'm going to do with the last part is do a kind of a fun little demo, and I can talk a little bit about the technology behind it, but I mostly just want to use it as an excuse to show this demo. So does anybody want to ask questions about crowdsourcing?
Yeah, so when you batch these tasks together, how do you vary the cost? Is it like the same, or is it like sub?
Yeah, so it turns out there have been a lot of studies where people looked at people's price sensitivity to tasks and the difficulty of tasks. And there are some rules of thumb. In our evaluation, what we did is we fixed the cost of tasks at, I think, 2 cents a piece. And then we just looked at basically at what point do quality start going down or the latency. Like the way, I don't know if you guys have used Mechanical Turk, but the way it works is workers see a list of tasks that are available, and they see they can, basically these tasks are grouped together. So like in our case, we would say there are 1,000 hits that are Adam Marcus's ranking task. And you could pick one of these hits up and do it. So people might do one, but if it took them a long time, they might not come back and do another one for 2 cents. And so you can see what the latency is and the rate at which they're completed, and we measured some of those things. There have been other people who have looked at, well, what if you adaptively vary the price? These experiments turn out to be kind of maddening to run because you don't have any reproducibility. Like the set of people who participate one time is different than the set of people who participate later. And in fact, the set of people change, the sort of people who want to do your tasks is biased by the kinds of questions you've asked in the past before. So the workers have these like forums that they talk about task posters on. And so, one of the problems that Adam had is when he first started running this, he started doing some things that the workers didn't like, and they said bad things about him, and then his reputation was bad, and people didn't want to do his tasks. And then later he came back and managed to get some people to say nice things about him, and they did all his work. But you can imagine how hard it is to get reproducible experiments in the face of this kind of a human system. So.
All of the people who are doing these tasks?
There are quality controls that Amazon provides. So one thing you can do is you can say, I only want to use people who have successfully completed at least X of these things in the past. They have a certification. They have like a master's certification. You can ask them to, you can limit the tasks to. There's lots of different things you can do. In some of these cases, we were actually interested in understanding. We looked at some problems like, could you build systems that are robust to people trying to game or spam the system, right? So could you ask questions in a way that prevented people from being able to, significantly skew the results or cause the system to provide answers that don't make any sense? So, but if you use some of those quality controls, maybe you can make some of those spammers go away if that's what you want. Right. Yeah, it still though is like it's not. I mean, you don't have any way to say, I want to send this to these 100 workers. You can just say, I want to make it so that this category of workers is not able to complete this task. So you can't, there's not a way to specifically recruit the same workers over and over and over again.
Is the research on this problem primarily in the database field, or have you found that there are other areas of CS science that have also been looking at this?
So there's some HCI people who've looked at interfaces, and there's been some social science and economists who've looked at, various aspects of this problem, incentives, and yeah. So it's not just a bunch of database people. I would say, in fact, that there's a group of people at MIT who have been doing this HCI work in the space who built some really pretty nice interfaces and tools. I don't know if you guys have seen. Michael Bernstein's work. He was just hired at Stanford. He built this really cool system for using crowds to summarize documents, and it was like, it's a really nice and proofread document, so you can take your research paper and it decomposes the paper up into a bunch of sentences and asks each sentence to a crowd worker, and they, the crowd workers all suggest edits and fixes, and then there's another crowd worker who's responsible for verifying the fixes and saying, yeah, this or voting, choosing which of the fixes is best. And anyway, they said for $12 or something, and 8 hours you can have your entire research paper proofread. And in fact, it finds the obvious grammatical mistakes. I mean, the results are, you don't get beautiful prose back, but it does fix errors. So it's certainly better than Word. Yeah.
How big do you expect this kind of system will finally handle the size of the task?
It depends a lot on the, I think this actually probably is most relevant in reality is in organizations that have relatively large groups of people who may need to, collectively contribute to something, or, collectively, make decisions like order things or rank things. I mean, you could imagine in an organization like, an engineering group at Microsoft that might have hundreds of people in it, that, there's certain kinds of tasks that would be interesting. Or, maybe expert finding inside of organizations. Who's the person at Microsoft who knows about X, Y, or Z? And, it's not quite a database problem, but it is sort of a, how do you, sort of a crowdsourced computation problem. I mean, how big will this scale to? I mean, we ran up to, databases of thousands of elements in them. I mean, so it's not scaling to billions of things. It's never going to happen, right? So.
Data tamer people.
This particular work, I mean, the data tamer does have a crowdsourced component to it, and I think data integration is a natural place where you want to try and use crowds to help you answer some of the questions. So they're using some of these things. I don't know that they have a need for a ranking interface, but you could imagine that it might be something you would want at some point. I mean, I think data integration is an obvious place where you want to integrate crowds. They have a model. They claim that they have experts who are doing this, so they've been working with genomics and genetics companies, and there they want to use people who really understand what is a this particular column in the database that has some genetic significance. What does it mean, right? And so you can imagine there that using Mechanical Turk might be difficult. All right, so with the last few minutes, I'll just talk quickly about this MapD system. So this is a system that somebody named Todd Mostak, who's not actually a graduate student but is a programmer working with me, has been building. It's a GPU-based graphics visualization system. It's actually underlying it is a SQL database system, but the manifestation of it is this interactive visualization system that the demo I'm going to show is running on top of Twitter. So why are GPUs interesting? So I sort of for a while, I don't know how many of you guys are doing work on GPUs. I know there's some people here who are actually probably building a system that kind of looks like this. But I sort of for a while, my take on GPUs had been, well, you see these papers where people like, I have a hash join implementation that runs on the GPU, and the performance on the hash join itself is awesome, but you have this problem that you have to transfer the data out of the, out of the CPU onto the GPU, do the computation, and then transfer it back, and you end up, with a, net gain of 20% or something. So our take in MapD is that these GPUs are becoming increasingly they're getting larger, more and bigger, such to the point that where you can now buy GPUs, a single card with 8 or 16 gigabytes of RAM, which means you can put, say, 12 of these cards in one box. So now you can talk about a box that can host, hundreds of gigabytes of data and so you can start talking about having terabytes of data on, small numbers of servers, which is probably interesting. It's at the point where, if you were a government agency, for example, that had a, terabyte-sized data set you really wanted to interactively explore, it would make sense to start thinking about this kind of technology. So that's what we're doing in MapD. We're basically building a parallel database system that it's a column-oriented parallel database system that basically lets you load certain columns into the memory of these GPUs and then run queries on them inside of the GPUs. So, and it has some interesting compression and other techniques to try and take advantage of the data that's available as much as possible. the sort of awesome thing about these GPUs, which maybe some of you know and maybe some of you don't, is that these things have an incredible amount of parallelism inside of them. So the GPU programmers talk about cores, which as I understand it aren't quite the same thing as CPU cores, but they talk about core counts in the 4,000 cores per GPU. Okay, so we have a level of parallelism that just goes way beyond what you would get out of a conventional processor. And the bandwidth, the intra-GPU bandwidths are higher, significantly higher than on a CPU, although not orders of magnitude higher. They're like 2 to 3x the bandwidth that you would get between the memory and the CPU in a conventional architecture. So that's going to mean that we can get cool, pretty remarkable interactive performance out of these things. So I'm just going to show you this demo. I can avoid falling on my butt because this chair is missing a wheel. I'm going to show you this demo over Twitter. So hopefully you guys can all see. So this is a map of the United States. So these are, it's going to be a little bit unresponsive because we're coming over Wi-Fi to a server on the East Coast, but we can do this interactively query. In this case, it's I think 100 million, about 100 million tweets that we have loaded, which is over a couple weeks of data. We can get about 30 frames per second. So what we're doing here is none of these queries are pre-computed. We're exhaustively scanning all 100 million tweets to evaluate every query that I'm about to show you. Okay, so the system. I'll just give you one simple example. We can ask a query like, tweet text, I like rain. Okay, so those are all the tweets that have rain in them. You can click on one individual tweet, fishing, and it's kind of chilly standing in the rain, right? So you can see the text of an individual tweet, but more interestingly, you can build this kind of a heat map visualization, which shows the relative frequency of the word rain versus the background frequency in each region. So we can render this heat map, and then we can interactively visualize it. So now we're animating frame by frame. Again, each frame here is being generated by a sequential scan of the whole data set. But you can see these rainstorms as they move across the United States in this animation. So hopefully. Well, this was in, I don't know, when does it stop raining? When does it stop raining in Seattle?
7 days in July.
You've had a good couple of weeks. Yeah.
24 days, no rain at all.
Yeah. Well, so this is late May and late April and early May. So it looks like it stopped raining. People kind of stopped complaining about it over here by mid-May. So, all right. So, but there's other sort of interesting and surprising things you can discover from this. So here's just another simple example. So if we type Central Park, well, you see Central Park lights up there. There's also apparently a Central Park in Maine somewhere. But you can zoom in on this, and you can see, in fact, it does a pretty awesome job of localizing Central Park, right? That's exactly because, well, what do people do? They go to Central Park, and they tweet about it, right? And I'll give you one more example, and then I'll stop and let you guys ask a few questions. I like this one, which is, let's see if I can, I typed Red Sox there. So for those of you who don't live in the Northeast, you may not know, I don't know if there's a similar effect here, but that there's this kind of imaginary line that runs kind of diagonally from through Hartford, but between New Haven and Hartford, that sort of is the dividing line between Red Sox fans and Yankees fans, or Patriots fans and Jets fans, or whatever it is, and you can actually use this to kind of visualize it. So if I switch this to Yankees, you'll see that it switches over the other side. So I'll leave it at that. I am pretty excited about this system just because I feel like it gives us, you can see why having this kind of interactive ability to explore a large data set is really pretty awesome. It's the ability to run these kinds of analytic, sequential scan style queries on large data sets in milliseconds is a capability that is surprisingly powerful, and it's one that I think existing analytic database engines probably really aren't optimized towards. People haven't been thinking, millisecond latencies. People, say, well, a second latency would be great, right? Or if you're in MapReduce, you say a 30-second latency would be great, right? And those differences are, although they sound, in absolute magnitude are small, you can see why in an interface like this, even that little bit of lag that we're getting going over the Wi-Fi network to the West Coast makes the experience not as nice as it is when you can do this on the East Coast. And we're looking at a bunch of other kind of analytic style things in this visualization space we can do here. So, questions?
There is this GeoFlow in Excel. Partly from research machine. Maybe the difference in the volume, or
yeah. So I'll actually say the reason that this guy built this system to begin with. I don't know about GeoFlow. I don't know. I haven't tried it. My guess would be typically things with Excel are not. It's not designed to scale to hundreds of millions of points, although I know that there have been some cool extensions and research results that have come out lately where people have done really neat things. But
power pivot for Excel.
Yeah.
Because the whole point was you could do sorting, filtering, pivoting
right.
on hundreds of millions of rows in Excel.
Right. Which is
a specialized engine built just for that.
Sure. Yeah. So I think obviously I don't think I'm not so much saying that these kinds of visualizations. I think I like the interface we built, but I'm not trying to claim the interface we built is what's exciting about this. What I think is exciting about this is the ability to use these GPUs in a really efficient way to do this kind of computation. And again, when it comes down to when we go write research papers about this, the research papers are going to talk about all the tricks we had, the convoluted little things we had to do to get good performance on these algorithms and compress the data in a way to load as much data in as you can get. You can kind of imagine all the systems challenge, moving stuff on, these columns on and off of the thing. There's a bunch of systems challenges that you have to deal with in order to build a system like this.
So let's go back to the envelope calculations. You said there's 100 million tweets?
In this over 2 weeks, this is 2 weeks, there's about 100 million tweets that are geocoded.
So how big or how the maximum size of a tweet is?
It's complicated. So it's 160 characters, right? So what is it? 140 characters, sorry. Yeah, but there's metadata, so it's, and then it compresses some. I think you call it a kilobyte would be a good, I believe that the records that Twitter sends you are on the order of a kilobyte because
100 million is a terabyte?
100 million
is 100 gigabytes.
The raw data of 100 billion would be, sounds like 100 gigabytes, right?
How many cores did you have?
In this case, we're using, I think, 4 GPUs each with 8 gigabytes of RAM, but we're not loading, so the trick is that we're compressing the text because there's a lot of repetition in the words. We don't actually need, I called it a kilobyte, but when it's a kilobyte because it's like they ship it to you in some JSON format and they've got like the, ASCII text of the person who posted the name and ASCII text to represent the Latin long. And, there's a whole bunch of, kind of goofy encoding tricks that you play to make it.
Do you have a sense of kind of what the speed up is from all the techniques that
so
you're
we're
using
actually getting, we've got these,
just pumping the data in raw through the GPU?
We've got these, okay, so I thought you were going to ask how much faster is it than a CPU?
Well, no, pumping data through the GPU is generally the thing with GPU processing in the past for any kind of database operation is it costs more to get it in and out.
It's the copying it in and off, right? So you can, whatever it is, you get your 3 gigabits a second or something right into and out, right? And so that is the gating factor to copy. If you're streaming the data in and then streaming the results back to the CPU.
Good number.
3 gigabits a second is. It's an okay number, but if you have
is that
30 gigabytes of data, it's going to take you.
No, I'm just saying that's roughly.
I think 3 gigabits is PCI. I don't know. So you guys probably know better than I do. 3 gigabytes is PCI bus bandwidth, okay, right? I mean, maybe these GPUs have a little bit better than that now, but it's not. It's not a ton better. So the question I thought you were going to ask is how well could you do in a carefully optimized main memory implementation, which I think is a pretty interesting question. We have these guys at Intel who are working with us who basically were porting this thing from GPUs to CPUs, which sounds a little bit silly, but they're these high-performance computing guys who
should be running this on board, right? I mean, you've got the GPU with local memory.
Yeah, so interesting. Intel has this thing, this Xeon Phi board, And the next generation Xeon Phi is going to be an it's going to be a coprocessor located right next to the CPU or even in the CPU that is like sort of like a graphics processing unit that could be used to do. It has much higher bandwidths than the PCI bus does.
It's how much data you transfer. Let's say you have a 4 GPU, right? So each one has basically PCI bus, and it's the 3 gigabit per second.
So the trick here is we're not transferring any data. The data has been pre-loaded into the GPUs, and that's, at some level, that's the trick, which is we're saying let's load the data that we want to query into the GPUs, and then we can, in this case, the tweets, and then we can interactively explore that data.
So then are you using the GPUs for actual rendering the task at all, or no, it's just pure?
So the current implementation that's drawing those heat maps is not actually using, kind of ironically, not actually using the GPUs to draw those things. It turns out that for whatever reason, rendering these PNGs that get sent back over the web is something that the GPUs are not good at. So they're good at directly rendering to the screen, but because we need to send data back as these compressed encoded pixels, that's something that is easier to do on the CPU. So we basically send a histogram to the CPU, which then computes the graphics. And in fact, if you look at the latencies per frame, something like half the time of each frame of this animation is spent doing the rendering of the PNG that gets sent back. So.
The operation you showed here was big, which is sort of massive.
Yeah. Yes.
What are the operations?
So we have an implementation of group by that he was trying to get in place for the demo, but basically a way where you can do a spatial aggregation, so you can group by region, and then compute distributions, so you can compute like the top K trending words in every region, for example. So that requires you group by region, and then within each region you can compute an aggregate like the top K, and then you can do differences between adjacent aggregates. So we can do that SQL query, for example. There are certain cases where key value, sort of key foreign key joins would obviously be useful, like you want to look up some metadata about some particular thing. We don't have that implemented, but it's something we're adding. So for example, like if the tweets have images references in them, you might want to go do a lookup to an image table and display that. Although we probably would actually do that on the CPU. It starts to when you start thinking about these, now you have to think in this world of split execution, where it's like, is this something that makes sense to do on the GPU, or do I store these images on the CPU or even on the disk and just fetch them when the user asks to render them? But I think this idea of being able to render hundreds of millions of points, like we're literally drawing 100 million points on the screen here, and it's like it's pretty cool. Like it's a big data set. And this guy who built this, he basically built this because he was a Middle Eastern Studies major at Harvard, and he was trying to get ArcGIS to let him visualize tweets in the Mideast, and he was pissed off because ArcGIS fell over at 10,000 tweets or something, and so he went and built the system and showed up in my database class one day. I built this, so that's why we started working on it. Anyway, so that's basically all I have, guys. There's a little bit more about those things, but happy to take more questions.
Thanks.